Does anyone want to ask any homework questions?
Well, since I've submitted it, I'm just going to go with...
Okay. All right. Whatever you got to do.
Yeah. I'm either right or damned already. So.
Okay. Yep. Anyone else? No? They're all easy? You haven't started yet? Okay. Well, that's good. Yeah, I was just talking... looking at the problems with someone else in the class, and I realized that I guess these things those ones are kind of tedious in terms of inner products to compute and heavy use of trig identities. So that's going to be interesting when I go to pick the problems for midterm. Now, okay, there'll be one more assignment that will be due next Monday, October 1st, that is also on Chapter 1. And then there'll be another one that will be due on part of Chapter 2 that will be due October 8th. But I think I'm going to limit the midterm to problems in Chapters 0 and 1, just so all that's had some time to sink in. I will base the problems on the homework problems. Of course, I have to check on time, make sure I don't, because some of these problems take a while to write out, and so I have to keep that in mind for a 90-minute test. So I'll figure it out. So there might not be many problems. So we'll see. I haven't even started writing that test yet. So the midterm will be, my apologies, the Wednesday before fall break. And yes, to make it worse, I won't even be here. That's why I put it there, because I was traveling over fall break to meet one of my colleagues out in California. So
that's cool.
Yeah, so I thought, well, I need the Wednesday also to fly. So I will enlist someone to be here to administer a test. So, man, that's looking bad. No rain's coming in through that window, but okay, all right. Alrighty. Wow, we are not on Chapter 2. Okay, sorry. We're still on Chapter 1. But this is the last class. Okay, so we look at convergence of Fourier series. Now, what we're going to get into today is uniform convergence of Fourier series. Now, we've seen uniform convergence of sequences of functions before, but now we can focus on this specific case of Fourier series. So I'll start with a theorem in a simple state and a bit less simple to prove. Well, they all are, I guess. I'll cut the Pythagorean theorem. But, okay, so F it's continuous on minus pi to pi. So that's what that means. F is in the space of continuous functions defined on minus pi to pi. And we also assume it is at least piecewise smooth. So it does not necessarily have a continuous derivative, but it's close to its first derivative is at least is piecewise continuous. Okay. So if that's true, then the Fourier series converges uniformly. On the interval minus pi to pi. Okay. Okay. Now, following the book's lead, I'm going to do a bit of a cop-out here. that we're going to. I'm not going to prove this theorem as it's stated, but with a weaker assumption. And now, lazy am I. So I'm going to assume for proof that f is in C2. So it's twice continuously differentiable on the minus pi to pi. Okay. Now, let's see. So what we have here is set some notation. So f has, I don't think it helps, probably not. So the usual Fourier series. That's A0 and then sum of AK cosine KX plus BK sine KX. And then, as in the proof I did last time, we look at the truncated Fourier series, because that's what we want to see converge to F. So same thing, I'm just going to stop the sum after capital N terms. AK cosine KX plus BK sine KX. I'm trying to get the habit of saying what I'm writing because I know people can't read my writing, especially if they're watching this on YouTube. Okay, so what we want to see is what happens to the error, because we want to make sure that this error, f minus Sn, goes to 0 uniformly on minus pi to pi. Okay, so now the error, we're going to have some cancellation here of the first n terms of a sum and also the a zeros. So all that's left is going to be the summation from n plus 1 up to infinity. It's getting worse and worse. Okay. So the error, f minus Sn, is just a sum from n plus 1 to infinity. Same old terms. Proof is feeling competitive already. Okay. Now, using the assumption that this is twice continuously differentiable, we'll look at the second derivative. So, when we take the second derivative of this, with cosine, second derivative of cosine kx is just minus k squared cosine kx. So it's going to give us a factor of minus k squared times everything else. Now, here's where we use the fact that we're assuming, as part of this cop-out, that f double prime is, that f is twice continuously differentiable. So now, because f double prime is continuous, this series has to converge. Actually, really what we know is, f double prime is continuous, then what we have here is that, k squared ak and k squared bk have to go to 0 by the Riemann-Lebesgue lemma. reason why we know that is really what the Riemann-Lebesgue limit tells us is that the inner product f double prime with cosine kx or sine kx has to go to 0 as k goes to infinity. But what is that value of the integral? It's minus k squared ak times something, or minus k squared bk times something in the case of sine kx. So because these integrals go to 0, which are related to, and these integrals are related to these inner products, these coefficients therefore must also go to 0. As k goes to infinity. That's the important thing. By the Riemann-Lebesgue lemma. Okay. All right. So now what we can say is that k squared ak, also k squared bk, must be bounded by some number m. And the reason for that is a convergent sequence is bounded. Yeah. So now what we can do is say the following, that the sum of AK plus BK, well, each one of these terms individually is less than or equal to m over k squared. So this is less than or equal to the sum of 2m over k squared. And this is a convergent series. So this sum is finite. Well, we actually know that it's m pi squared over 3. That's something that will come up later. But the point is, it's finite. So in other words, the sum of these coefficients in absolute value, so this is an absolutely convergent series. Now, so I'm going to use the convergence of this series to show uniform convergence of the Fourier series. And for that, I'm actually going to use a lemma that's going to finish off the proof of this theorem that I started. All right, any questions up to this point? Yes?
Here you got like k square ak and k square bk less than m.
Yeah.
Like you got the maximum of.
Yeah. Each one of these is less than or equal to m.
Okay.
Yeah. I was too lazy to write two inequalities.
Oh.
Yeah. Okay. All right. And because each one is bounded by m, that's what led to the 2 here. Okay. So. All right. So now in the notes, this is presented as I'm proving his theorem, and then I say, oh, the result follows from this by a lemma that I have right after this. So I'm just going to do it all as one thing. Okay. So at this point, I've not yet talked about uniform convergence. We have a definition of uniform convergence. Now I'm going to use that definition. Okay. So I can let epsilon greater than 0. So I can say because this series AK plus BK converges, I could say that there exists some value n naught such that for n greater than or equal to n naught, the difference between this series and its sum, whatever its sum is less than epsilon. So that would just be the sum from n plus 1 to infinity. Okay. All right. So there exists an n naught such that if n is greater than or equal to n naught, then this is true. And that's just what we get from using the definition of a convergent series. Okay. So this is the sum minus the partial sum. Okay. And that's just all the leftover terms from n plus 1 to infinity. Okay. Now, but the thing is, if you look at our error, absolute value of f of x minus Sn of x, well, that is equal to this sum from n plus 1 to infinity of ak cosine plus bk sine. But cosine and sine are bounded by minus 1 and 1. So this is less than or equal to the sum from n plus 1 to infinity, ak plus bk. But that's less than epsilon from my previous step. So this is first of all, it's established point-wise convergence of the Fourier series to f of x, because for any epsilon greater than 0, there's an n naught such that for n greater than or equal to n naught, the error, the error between the f of x and its partial Fourier series is less than epsilon. Therefore, as n goes to infinity, this error is going to go to 0. But I can say something stronger than pointwise, because notice this n that makes all this work has nothing to do with x. It's not influenced by x at all because of cosine and sine being bounded by 1.
Yeah.
So n naught is independent of x. So this fits the definition of uniform convergence. And that's the end of it. All right. So, if you're able to show that the coefficients of the Fourier series themselves, without the cosine and sine, and show that those form a convergent series, which we did in this case, that's enough to show that we have but that's sufficient to show uniform convergence. Now, something to think about here is what I showed was that these Fourier coefficients are individually bounded by something on the order of k to the minus 2. So by showing that the coefficients to k to 0 at the rate of or k to the minus 2 or faster, we show uniform convergence. But if you look at our original assumptions, f is continuous and piecewise smooth. a function that is continuous and piecewise smooth also has Fourier coefficients that decay in the order of k to the minus 2. So that gives you an idea as to why this result, while I proved it only for a case of f twice continuously differentiable, would actually apply to these assumptions. Because what does it depend on? It depends on that decay rate. That the Fourier coefficients go to 0 on the order of k to the minus 2, that is good enough. Because if f really is continuously differentiable twice, its Fourier coefficients decay to 0 much faster. In the order of, like, if the second derivative is continuous and the third derivative is at least piecewise continuous, then you get order, let's see. So, order k to the minus 3. So it's just that when you assume that f double prime is continuous, it's particularly easy to reach that conclusion. It's not as easy with the original assumption. So, but then it could be. I think I know how I would do it. So I just don't feel like doing it now. I may add it to the notes later. So I don't have to cop out after all like the book did. So. All right. So any questions about what happened here? The key is being able to bound this independently of x. That's what lets you go from pointwise to uniform convergence. Okay. All right. So you see pointwise convergence, and here is uniform convergence. There's one other kind of convergence. That's convergence in the mean, showing that this error goes to 0 in L2. Now, it's actually a weaker form of convergence than uniform. The function can converge in L, sequence can converge in L2 and not converge pointwise or uniformly. But what I'm going to do here is prove convergence in the mean for a Fourier series. So actually, just for functions in L2. So f doesn't even. So the nice thing is you can establish convergence in the mean for a larger class of functions. Here we needed continuity, or convergence definitely would not happen. But even if we have piecewise continuous, for instance, so this is a function as in L2, so it has jumped its continuities, we can prove convergence in the mean. Like clean this board daily, or maybe hourly. Okay. All right. So I need a lemma. Set this up. So I'm going to work with a vector space L2 minus pi to pi. And I'm going to define a subspace of V to be the span of functions up to frequency k. So 1, cosine x, cosine 2x, etc., up to cosine nx, and also sine x, sine 2x, up to sine x. So cutting off a Fourier series after n terms. So then, and I'm going to assume that f is any function in this L2. Then, if I define this function just to be the truncated Fourier series of f, cutting off after n terms, then this function fn is your orthogonal projection. En. So in other words, the chalk broke into 3 pieces, so it only makes me 3/7 of a Jedi. Okay, so now now I'm not going to go for like a full-blown proof of this, but I can explain why. So then you can show directly that f minus fn the errors are orthogonal to any function in the subspace. Because f minus fn would consist of all the other terms in the Fourier series, for k going from n plus 1 to infinity. But those sines and cosines are orthogonal to these sines and cosines. So because the error is in the orthogonal complement, that's what makes it the orthogonal projection. So by using the properties of orthogonal projection, we can see that this is a projection. Okay. So now I'm going to use the fact that this is a projection to show convergence in the mean. See if my time for the more interesting proofs. Okay. So the theorem is that so I use the same definitions. So I still have Bn, I still have Fn. Then Fn converges to F in L2. All right. Now, I'm going to use another lemma to help me prove this. I'm not going to prove a lemma. It's something that's beyond the scope of this course.
But what course will it be in the scope of?
Well, this is the highest number course, so this is that's the number universe. That reminds me, we had a couple years ago, we were hiring faculty members, so we had a candidate from Russia who had a degree beyond PhD, and apparently just having that degree is kind of equivalent to full professor in the US or something like that. I was like, oh my god, I'd like to try to get one of those. I don't know how that works, but yeah. He had like 200 publications or something. Okay, so we didn't hire him, but still. But the problem is,
was he like 70 or something? How do you remember?
well, he was older, but and his records were so old, it was hard to get a hold of anything because it was Russia. And,
anything spans the collapse of the Soviet Union.
Because my advisor, G. Gullib, had. He cracked 100 mark. Well, okay, we've had 2 faculty members in this department crack the 100 mark, and it's no surprise, Dr. Ding and Dr. Shen.
Yeah.
We're still only slightly above 100, but
still 100 mathematical papers is a pretty amazing
I know,
accomplishment.
I know I feel like a schlub by 26. But
Well,
my students. Well, helps launch your career too. Okay, so if F is in L2, L2, so that means that so even if F itself is not smooth, f can be approximated arbitrarily closely, so to within epsilon, for any epsilon greater than 0, by a smooth 2 pi periodic function. At least when I say close, like in the L2 sense. Now, to give you an idea why, like let's suppose you have a function that has a jump discontinuity, so not even continuous, let alone smooth function. But what you could try to do is where I wish I had colored chalk, but you could try to make a smooth curve that very abruptly dips. So the tangent line is not vertical. It looks vertical on my drawing, but not quite there. And there's a smooth bending, so there's no corners either. So it has a derivative everywhere. And if you're trying to approximate this to a bit epsilon, you just make this even steeper and steeper. And you can always stop just short of infinitely steep. There's some pictures in the book that describe this too. So it may still not be very well behaved. So you can have some very sharp derivatives in there, but it can be done. Okay. All right. So I'm going to back to the theorem. So I choose some epsilon, however small it might be, and let G be a 2 pi periodic smooth approximation of f, with this condition that f minus g be L2 norm is the most epsilon over 2. Okay. So we know such a G exists by the lemma. Boy, that's convenient. Okay. All right. Now, and then we're going to assume that Fn and Gn are the truncated Fourier series of f and g. Okay, so we'll work with both of those truncated Fourier series. All right. Now, now, G is smooth. So what that means is, so because G is smooth, Gn converges uniformly to G on the interval minus pi to pi. That's the theorem that I proved earlier that gives us this result. So we don't know if it applies to f. It may not apply to f, but at least applies to G because it's smooth. Okay. So what that means is there exists an n naught such that for n greater or equal to n naught, that at least on a pointwise basis, G minus Gn is less or equal to, so I'm going to pick this seemingly arbitrary expression, epsilon over 2 squared root of 2 pi. And the reason I do that is that the norm of G minus Gn, the L2 norm, which is equal to the integral from minus pi to pi of, okay, it's less than or equal to the integral of this difference. Okay, and I hope I picked my expression right. It's possible I might not have. Okay, we'll see. All right, so now we have epsilon squared over 8 pi squared. Okay, so epsilon squared over 8 pi squared, which is, but this is over interval with 2 pi. So now we multiply by 2 pi. I'm sorry, this is under the square root, so that should just be pi, not pi squared. Okay, so then I get epsilon squared over 4. Okay, actually that is what I wanted, so glad I did that right. This is a L2 norm squared, so therefore the norm of g minus gn in L2 is less than or equal to epsilon over 2 again. All right. So what this means is, we look at this L2 norm of f minus fn. Now, actually, I don't need to square it. Okay. Now, I'm trying to establish that this norm goes to 0 as n goes to infinity. So for this choice of n naught, so in other words, actually I need to be more careful about this. Well, actually, no, I don't. I've already been careful enough. So this is the n naught I need here. Now, Fn from the lemma earlier is the orthogonal projection of f onto Vn. Therefore, this is less than or equal to f minus Gn. Because Gn resides in the same subspace. It resides in Vn. But this approximation has to be at least as good as this one, because this is the best one, being the orthogonal projection and all. Okay. Now I can work with this. So this is less than or equal to L2 norm of f minus g plus g minus gn L2 norm. But both of those are less than or equal to epsilon over 2. So the norm of f minus fn is bounded by epsilon, and that settles it. So that means that Fn converges to F and L2, because we're showing it to norm. The L2 norm of F minus Fn goes to 0. Okay. Because we picked any epsilon, and we showed that if n is large enough, that norm is smaller than that epsilon. So that's the definition of convergence in L2. Okay. Yeah. So I saw in textbooks do something like this, like they pull this out, like, why? And then you see why. Yeah. So as a student, it's like, I want to do that. Like, oh. Okay. Questions about this? Okay. All right. I have a similar theorem that is not worth spending time on, really, just because it's so identical to what I just did. But I showed you that the real form of the Fourier series, of the combination of cosines and sines, converges in L2. The complex Fourier series also converges in L2. So that's actually the next theorem in my notes here. So with the definition that's been given for that previously, the proof would work out exactly the same way, using the same lemma and all that. So I'm not going to bother with that, especially when there are more interesting results to work with. Okay. The theorem is stated in the notes. Okay. All right. So we have the real form and complex form of a Fourier series. And then the complex form, which we haven't used today, but alpha k e to the I kx. This is on minus pi to pi, as usual. Okay. Now, the real and complex forms of the Fourier series satisfy an interesting identity called Parseval's identity. See, mathematicians like Parseval and others who had things named after them, they had it so easy. They had to just prove something that I'm going to be able to easily do right here, and they get this named after them. So.
But we do have to say that it's a whole lot easier with our notation than with some of the earlier things.
Oh yeah.
I mean, and one of the things I think is really fun, I think every mathematician should do, I'm sorry for the tangent, is actually read diaphanous.
Oh, okay.
Just even sections, because you discover things like even commutativity of algebra is not assumed.
Oh, wow. Okay. Well, when Newton developed calculus, it didn't have the epsilon delta definition of a limit yet.
Yeah. So, Parseval might not have as we might want to think he was.
Okay. Fine. Okay. So what this says is, okay. So there's a real and complex forms. The real form is that, so 1 over pi times the, I forgot to write this in the note, this is the L2 norm, that's squared, is just equal to this combination of the coefficients, the sum of squares of the coefficients, except for A0 you have to double it. So it's almost like if you treat the Fourier coefficients as a sequence in little L2, except you count A0 twice. That should be squared also. Then the norm of f in big L2 is equal to the norm of coefficients in little L2, except for this factor of 1 over pi here. Even the complex version is that it's 1 over 2 pi L2 norm of f. Actually, I'm going to make a note to myself there to indicate that this is L2, even though we haven't been working with any other norm, but still, completeness. And that would be the sum of all the complex Fourier coefficients squared. Okay. Oh, this is squared too. All right. So it's basically this invariance of a norm between physical space, where it's a function f of x, and frequency space, where it's the Fourier coefficients. And there's a result related to one for a complex form, be a little more cumbersome in the real case. That if you look at the inner product of two functions, f and g, and in terms of their, you can take the inner product using the integral, or you can take the inner product of the, like, treat their Fourier coefficients as vectors. So the alpha k's are the coefficients of f, and the beta k's are the coefficients of g. So, so you can either take the L2 inner product in physical space, treating as functions of x, or in frequency space with vectors of their Fourier coefficients. And this is something that's extremely useful when working with Fourier series in general, that you can take the inner product in either space. Because what if f and g are combinations of only a small number of terms in their Fourier series? Then you can take their inner product much more easily. I'm just matching up these coefficients. Okay. So what I will do is I'm going to prove this. And by proving this, if you just let g equal f, then that would follow immediately. And then by looking at like real and imaginary parts, you would be able to prove this from that, but I'm not going to take the time to do that. Okay. Oh, and then I'll be almost done for the day. Okay. All right, so partial proof. So if I take a look at the inner product, Fn Gn. Okay. So that would be integral from minus pi to pi. And I'll just substitute in. So Fn and Gn are the truncated Fourier coefficients. So sorry, truncated Fourier series. So I'll just write these in here. So sum from minus n to n of alpha k, EVI kx, and then use a different index, L, little l, minus n to n of beta k, e to the I, beta L, e to the I Lx dx. Oh, is it still going? Okay. All right. Now, the second argument has to, it's a complex conjugate of that. Okay. Now, oops, I forgot angle brackets. Okay. Now, here we use the fact that the functions e to the I kx are orthogonal. So, all right, so if I were to pull out, use the linearity of the integral, the sum over k, sum over L of alpha k, beta k conjugates, and what's left is just the inner product, e to the I kx, e to the I Lx. But that inner product is 0 unless k is equal to L, in which case it would be 2 pi. Because you have e to the I kx minus Lx, and if k is equal to L, you just get 1. You're integrating 1 from minus pi to pi, you get 2 pi. So all that's left is 2 pi sum over k of alpha k, beta k conjugate. So orthogonality immediately leads to this result. So this inner product is equal to 0 if k is not equal to L, and it's equal to 2 pi if k is equal to L. Because you're just integrating 1 from minus pi to pi. I guess I should put a fancy brace there, like all the books do. Okay. Right. Oh wow, I keep forgetting my have so many syntax errors in my notes, if not mathematical errors. Well, I guess there's mathematical errors too. Okay. So now I have a nice expression for inner product of Fn and Gn. Now, if I look at the inner product of F and G minus inner product of Fn Gn, I need to show that that this goes to 0 as n goes to infinity. Okay. Oh God, what does Dr. Schroeder want? Oh, okay. All right. So using hocus pocus, the add subtract trick. So that'd be Fg minus, and I'll fill in inner product of F of Gn. So I'll subtract and add that. Minus Fn Gn. Okay. And then I'll break this up. So this is less or equal to inner product of F with G minus Gn plus inner product of F minus Fn with Gn. But here's where we're using Cauchy-Schwarz inequality on each term. So less than or equal to norm of F. So all these norms are L2 norms. It's just too lazy to put that in here. Norm of F minus Fn, norm of Gn. Okay. So the thing is, F is converging to Fn, Fn is converging to F, and Gn is converging to G. So, and norm of F and G are bounded because F and G are square integrable. So this goes to 0 as n goes to infinity. So what it's saying is that this inner product converges to this one, therefore the expression for it, the partial sum of the alpha k times beta k conjugate, converges to the infinite sum of alpha k times beta k conjugate. So that's what establishes this formula. Wait, move that a little more. This formula right here. And then if you just set f equal to g, then the formula to its left would also come about. All right, so, wonderful things you can do is immediate consequence of orthogonality. So, orthogonality is your friend. Answer any questions about what happened here? Okay. If I were to, okay. There's one other thing that follows immediately. Sounds like a typical snobby math book. It follows at one staff. Okay. Because since this is equal to the sum of all the alpha k's, from k minus infinity, and because we have a sum of squares, and it really would follow at one stat, that if I take a partial sum of the alpha k squares, then that is less than or equal to 1 over 2 pi norm of f squared. Because we're just taking part of this series. And I'm mentioning this, it seems like a silly result to write down after what we just had here, but this has a name, it's called Bessel's inequality. Okay. All right. So now, how are we doing on? Okay, we're actually doing quite well on time. So I'd have just an example, a fun example to wrap up with. Okay. because when taking calculus 3, well, it's calculus 3 here, maybe calculus 2 elsewhere, and you're learning about infinite series, there's only a couple types of infinite series you actually, and you're showing whether different kinds of series converge or diverge, but there's only a couple types of series in which you can actually compute the sum, like in geometric series or telescopic series. So here's one that also the sum is known. It's just never really discussed in Cal 3 because in Cal 3 the only question is, does it converge or not? Okay. Now, this function that we visited before, fx equals x, on minus pi to pi, we could actually computed its Fourier series. Now, Fourier series does not converge pointwise to f everywhere because this function, when you take a 2 pi periodic extension, is discontinuous every 2 pi. So we get Gibbs phenomenon, but that's not troubling us today. So these Fourier coefficients were computed in a previous example using integration by parts, or some might call it parts by integration. Sorry, I couldn't resist. All right, so what we're going to do here is we're going to apply Parseval's identity, because the real form you notice one I didn't prove. So Parseval's identity says that the sum of the absolute value squared of all the Fourier coefficients, so in that case, that would just be 2 over k squared. That would be equal to 1 over pi times the L2 norm of f. So that would be the integral of squared. The L2 norm squared, so that would be the integral from minus pi to pi of x squared dx. So we can just go ahead and evaluate that integral. Well, that's the same as the integral from, so 2 times the integral from 0 to pi of x squared. All right, okay, so you get x cubed over 3, and then you plug in pi, and what you get is 2 pi squared over 3. You get pi cubed over 3, and then times 2 over pi. Okay. Am I getting all that on the board? Yeah, all right. So now if I look at the first and last part, so now I have 4 times the sum of 1 to infinity of 1 over k squared is 2 pi squared over 3. So now I just divide both sides by 4, and I have at the sum of 1 over k squared is pi squared over 6. Right. So that's a very famous formula worked out by, I think it was by Euler. I think it's called the Basel problem or something like that. Anyone can correct me if I'm wrong. Or I can try looking that up. It's been a while since I've read about this. Yes, it is the Basel problem solved by Euler, that this sum is equal to pi squared over 6. Okay. All right, so, and Parseval's identity gives us relatively, I've seen other solutions to this problem that are a lot more long-winded than this. I tried presenting one in my Cal 3 class, and it was very painful for them. But I couldn't really talk to them about inner products and orthogonality and all that, so I couldn't use Parseval's identity. I had to do something else using only lower-level things, and it just takes a lot longer. But if you have something like this handy, you can establish this sum quite easily. Okay, so that's actually the end of chapter 1. Woo, we're really making progress now. Okay. I know we're 18 minutes early, but that's all I have. Woo. Oh, and it stopped raining, hasn't it?
It has.
Okay, well, that worked out beautifully.
It did.
Okay.
But that's kind of some of the problems with trying to prove these interesting things with a lower level math. It
Yeah.
can become a really big pain.
It
working
it
around
was.
the brilliant